Emanuela showed me, and I did not do a problem like that in class, and I would like to. So here's the problem that I would like us to start with. I thought I did, but maybe I didn't, because I don't recall this problem. So here, we are given a function, and we are asked to find the limits and then conclude or find the equations of the vertical asymptotes. Okay? So we're asked to find the limit as f of x approaches -7 from either side. What will you say? Do you all agree with -∞? -7 from either side. If one of the sides or both is +∞, -∞, or any combination, that is a vertical asymptote. Paul? 97. So x equals -7 is a vertical asymptote. We understand that. Yes? Everyone? Okay. We're asked to find a limit from either side of -3. What will you say? +∞, which makes x equals -3 what? Vertical asymptote. We're also asked to find the limit left and right of 0. So either side. What do you say? Infinity. Very good. What about 6 from the left? -∞. What about 6 from the right? Still, it's a vertical asymptote, but what about the limit from either side? Does not exist. They're all DNE because they're not a number. But I cannot write DNE if both sides go to -∞. I have to write -∞. I cannot write DNE if both sides go to +∞. I have to write +∞. And the same thing here, +∞, but here I have to write DNE if I'm asked from either side. So the equations of the vertical asymptotes, x equals -7, x equals -3, x equals 0, and x equals 6. Agreed? Any questions on this? Because this was a problem from your homework. Okay. I'd like to continue with some more infinite limits, and then we can continue with 2.3, limit laws. Okay, so we continue with infinite limits. And remember, everything is posted. The lecture notes, the videos, everything is right there. Okay. On page 98, I would like to look, I don't remember exactly. I think we only looked at one problem. So I'd like to look at maybe 36 or maybe 32. I don't care. You choose. But you only have 3 seconds to choose. 1, 2, 3, and then I will. Okay. 36 it is. It's only because I have so much to show you in this class, and I don't want to waste your time. Okay, so we have limit as x approaches 2 from the left of x squared minus 2x divided by x squared minus 4x plus 4. Remember, I keep saying when we talk about x approaches 2 from the left, we really mean it. X is not 2. But now I'm going to ask you to plug it in because there are several different categories of limits. So we need to know what type it is. So when we plug in, we get what at the top? Perfect. What will you get at the bottom? Good. So because we got 0 over 0, we say there is hope. Notice that I did not say there is any guarantee. I only said it could exist. I have no idea whether it does or not, but if it's 0 over 0 from the very beginning, it could exist. It has potential. If it is going to exist at the end, we'll have to investigate further. Okay, now, whenever in a polynomial, if we plug in 2 and we get 0, this is extremely important. It's a theorem that we will have to remember moving forward. I plugged in, this is a polynomial. I denoted it by p of x. And I plugged in 2, and when I plugged in 2, I got 0. What does this mean? It means that P of X has a factor of a polynomial cannot have a factor. I mean, it can have a factor of 2, but we're talking about x minus 2. So if I plug in -3 and I get 0, what is the factor of P of X? X plus 3 is that factor. Why is it so important to know? It's because I plugged in 2, and it's guaranteed that a factor of x minus 2 can go away with a factor of x minus 2 from the top with 1 from the bottom. This is the remainder and the factor theorem from pre-calc. So did they do it? Because I'm teaching now from this new book. Did they? Is that in there? From this new book?
Yeah, I want to say so. Yeah.
It is. Okay. I didn't get to that. So this is the first time I'm teaching it from this new. Okay. So when we plug in into a polynomial, when we plug in any number and we get 0, the remainder is 0, which means x minus 2 must be a factor of P of X. If we plug in -3, x plus 3, the remainder is 0, x plus 3 is a factor of that polynomial. So again, coming back here, what is important? It's important to know that if 0 over 0 is created by a factor of x minus 2, that has to go away. Both top and bottom have a factor of x minus 2, mandatory, because otherwise I will not get the 0 over 0. So knowing that, I'm going to continue here, limit x approaches 2 from the left, and I would like you to tell me how to factor the top. And you have to give me an x minus 2 in both. I know it's there, because when I plugged in 2, I got 0. It's mandatory. So look at the top and say, oh yeah, you can factor it, blah, blah, blah. Excellent. Yes, please.
Wouldn't it be x minus on the top, on the numerator, x minus 2, x plus 2, and the denominator is just x minus 2, 1, x minus 2?
Right, but see, the numerator, what you told me with x minus 2 times x plus 2,
Yeah.
but that's x squared minus 4. And I have x squared minus 2x.
Oh, okay.
So that's okay. That's okay. So we factor out an x, and we only have x minus 2. That x minus 2 was present for sure in both because of this 0 over 0. And now I can eliminate one of them. And the new simplified form is x over x minus 2. Yes, I have to plug it in again. So when I plug in 2, this time I get what? Okay, so there is no hope. So I know that the answer must be either yes or exactly. Thank you very much. So now we have to choose. It's 2 from the left. Please give me a number from the left of 2, very close to 2, and don't say -5 because that's not close at all. Like 1.9. The numerator, when I replace x by 1.9, still stays positive. When I replace it in the denominator x by 1.9, what do I get? Good. So then what is a positive number over a negative number, knowing that I must select from these 3? What do you conclude about x equals 2? What does x equals 2 represent for the original function of x squared minus 2x over x squared minus 4x plus 2? Excellent. Thank you. Notice that I did not investigate what happens to the right of 2. I don't care. If either one or both limits are plus or minus infinity, the answer is this. X equals 2 is a vertical asymptote. Any questions here? Any questions? Okay, so between now and Sunday, I want us to finish all the homework 2.1 and 2.2. Okay, that's your last chance for full credit. Yes, it's open till December. Yes, you can go back, but I want you to finish this so we can move on. Please. You can still increase your grade later on, but please bear with me and walk with me in the same direction at the same pace so we can accomplish what we want here. Any questions?
And you're talking like on WebAssign.
In WebAssign, please. Please. And don't forget to turn this in. I want to see it, and then you'll get another one. Because the difference quotient is half of this course. Yes?
Yes.
Okay, limit laws, 2.3. Kyle, you want some paper?
Yeah, sure.
What do you do when one of my best students comes to class with no pencil, no paper? What do you do?
It's not my fault.
Okay. You're going to see me next time. You're going to see two people running around the block, around the building. It's going to be behind Kyle. No. Just kidding. Okay. So moving forward, we do have some rules on finding limits. And the most important one I cannot present just yet till the end of the chapter, but I consider that the most important one. So I'm not going to explain anything about it because we can't talk about it just yet. We can't because we don't have the tools, not because we don't want to. Okay, so let's assume the following. That the limit of a function f of x as x approaches a from either side is L, which means it exists, which means the left limit and the right limit exist and they're both the same. Otherwise, the limit from either side will not exist, correct? We also assume that we have limit of g of x as x approaches a from either side, let's say, is a number m, which means the same thing, the limit exists. Then we can write 11 limit laws, out of which really only a few, less than 11, are something that we should think of. Several of them are really just common sense. I wouldn't even call them limit laws, but they are in the book, so I'm going to list all 11. Okay, so here's the first one. And the second one together. The limit of function f of x plus or minus function g of x as x approaches a from either side. So I'll put these two together instead of writing it twice. So common sense, what do you think this will equal to? Yes, the sum or the difference of limits. So limit of f of x as x approaches a, and limit of g of x as x approaches a. And of course, this will be L plus or minus m, because we have those numbers. I wouldn't call this the distributive law. I would not. I would just say the limit of a sum is the sum of the limits. I would say the limit of a difference is the difference of the limits. So here's an example for you. Let's say I want limit of 1 over x plus 2x as x approaches 0. Let's say from the right. Question is, can I write limit of 1 over x as x approaches 0 from the right plus limit of 2x as x approaches 0 from the right? That's what the law says. The limit of a function plus the limit plus another function is the limit of f of x plus the limit of g of x. The question is, can I do this here? The answer is no, because this is positive infinity. So we specifically said, when we talk about L and M, we mean that the limits exist. But this one does not. So I could not, and I'm not allowed to split it. This is not allowed here. Because the limit of 1 over x, and let me refresh your memory on the graph because we need this. So the graph of 1 over x, please remember it, is this. So then the limit of 1 over x as x approaches 0 from the right is infinity. And that prevents us from writing or using the limit law. It's not allowed because this is infinity, not a number. So be very careful. The assumption is that both functions have a limit, and the limit is a number. Otherwise, the limit does not exist. It could be infinity, negative infinity, it still does not exist, or DNE. If it's not a number, it does not exist. But we write positive infinity or negative infinity depending on the case. Questions? Is this clear? Everyone? Okay. Number 3. Limit of a constant times a function as x approaches a. Common sense, what do you think this would be?
The constant term.
Very good. Times limit of f of x as x approaches a from either side. Number 4. Limit of f of x times g of x as x approaches a from either side. Common sense, what do you think this would equal to? So the limit, yes, of f of x times the limit of g of x as x approaches a in both cases. Number 5. What do you think is next? Of course. And what is this answer? What do you think? Very good. But I have a big if now that I did not have before. If what?
It's not zero.
Exactly. If this is not 0. Because if it is, right, I cannot use the limit law. Questions? Okay, 6. Limit as x approaches a from a constant c. Now, I don't think that this should be a limit law, but it is. So what's the answer? What is the limit of 5 as x approaches 200?
It's just the constant.
Just a constant, of course. Who cares where x is going? The limit of a constant is the constant itself. Okay, 7. Limit of a function raised to the nth power. N is a positive integer. Integer. N is a positive integer. Now, this is a very important limit law because it uses a theorem that we need later that cannot be applied in all situations, so it has restrictions. It's limited to certain situations. But in short, I'm going to talk about the limit when we get to it in continuity. But in short, I'm going to say swapping operators. Just for us to remember it easier. It only is allowed only in certain situations, and the situations are based on continuity, but we don't have that concept yet. We will. So this is an operator, and so is this. It's the power. So I will put this operator inside, and keep this operator outside, meaning power n, limit of f of x as x approaches a. Yes, I'm sorry about that. I should have written here c times l. I should have written here l times m. I should have written here l over m, because we know those limits. And yes, I should write here l to the nth power. We swap the operators. The operator that was outside went inside to the function. As you see, this operator is closer to the function than the limit is, because I have to perform this first and then the limit. But now I put the limit close to the function and n outside of the limit. We swapped the operators. So here's another example. The limit of the nth root of f of x. If everything is continuous here, we are going to swap the operators again, and of course n is a positive integer. If it's even, of course, the quantity under the square root or the fourth root has to be positive. Of course, those have to be considered. So what do you think this will equal to? You notice that the nth root is closer to f. I have to perform this, in other words, and then apply the limit, right? But I'm allowed to swap the operators under certain conditions. What do you think the answer would be? The nth root of limit of f of x as x approaches a, which is the nth root of L. Nine, limit of x as x approaches a. Again, I don't think this should be a limit law, but it is, so what is the answer?
A.
Exactly. So here's the example. Here's the graph. When we graph y equals x, this is the graph. Y equals x, and let's say this is a. What do you think the limit will be? As x approaches a from either side, the function values will approach, you get closer and closer to what? Of course, because x equals y, y equals x. There is no other value. Is that clear? All points on this line are 1, 1, 2, 2, 0, 0, 3, 3, 4, 4, 5, 5, 6, 6, negative 1, negative 1, negative 2, negative 2, because y equals x. Okay, number 10. Again, this should not be discussed, but we have to. Okay. What is the answer? Again, I can swap the operators. I can say limit of x as x approaches a, everything to the nth power. And I know what this is. And the answer is to the nth power. Any questions? Any questions before we look at some examples? The other limit law that is number 11 is the same thing with the square root. So limit of the nth root of x. Again, I don't think that these should even be discussed, but same thing. We're swapping the operator. Limit of x as x approaches a. What will this be? So all these really are just repetition. So what is this? Good. So this is the nth root of a. Good. So now, before we look at a few other theorems here, I would like us to evaluate and determine, in other words, some limits. and I would like you to choose. We are on page 107, and let's practice some of these with some of these, like maybe 2, maybe 3, and then we'll go back to a little bit more discussion on a couple of theorems. 1, 2, 3. Okay, I'm going to choose 30. So this is 30 on page 107, and this is limit as x approaches -4 from either side from the square root of x squared plus 9 minus 5 divided by x plus 4. So this is a radical, and then we'll look at something else. We'll see, maybe a complex rational expression. Okay, we're asked to find this limit. What is the first thought? Mandatory thought. Plug it in. Please plug it in. Good. So what do you expect to remove from the top and the bottom for sure? Eventually. Eventually, if the limit exists. If it doesn't, that's a different story. Perfect. So we are after eliminating an x plus 4 from the top and from the bottom. We know for sure it's there because we plugged in -4 and we got 0. Although, you have to say, well, listen, I understand here, but I'm not really sure what you're talking about here because this is not a polynomial. So a few minutes ago, you were talking about polynomials, right? So all of a sudden, this is not a polynomial. Well, it may change into one. So we'll see. Perfect. What do we do? What mechanism, what procedure we are going to employ here? Awesome. Thank you very much. We multiply by the conjugate of the numerator, which is the square root of x squared plus 9 plus 5, the square root of x squared plus 9 plus 5. Everyone agrees? Any questions why? Are we okay, everyone? Perfect. Okay, so then limit as x approaches -4 from either side. I'm going to copy the denominator. And now carefully, please give me the numerator. X squared plus 9. Say it again. Indeed. A squared minus b squared, of course. This squared minus this squared. A minus b times a plus b. A squared minus b squared. We reviewed that on the first day of classes. Everyone agrees with this? Yes? Do I need to show anything? Don't be shy, please. This is very important. I'd rather go back and explain if there is something that you need. Is this okay? Okay. So then I have x squared minus 16 at the top. Ah, so it did change into a polynomial. As I was expecting it would. Good. What do you think about the top?
X plus 4.
Right. And as expected, from the very beginning, it happens, right? What is it? And now we give it another shot. The top goes to. The bottom goes to. Excellent. I will simplify top and bottom by 2, and I get this. So we had initially 0 over 0. We were not sure, but there was hope. And it turned out that the answer is -4/5. So the limit exists, and it is -4/5. Any questions? So what type of limit was this? A limit with a radical function in it. And we used what method, what technique? Of rationalizing the numerator. Rationalizing the numerator by multiplying and dividing by the conjugate of the numerator. We rationalized the numerator. Okay. So let's choose one more. One.
28.
Thank you, Kyle. So we chose 28. 28. Good one. So limit as age approaches 0 from 3 plus h to -1 minus 3 to -1 over h. Perfect pick, actually. So when you see something like this, what goes through your mind? Right. Right? Okay. As long as this is f of x plus h, and this is f of x. Or it can be f of a plus h, and this is f of a. We're going to get to that at the end of this chapter. Excellent. Of course, it's a difference quotient. Good. So what does 3 minus h to -1 mean? Perfect. If I don't identify that correctly, I will not be able to find anything here. Indeed, power -1 doesn't mean that the number is negative. It could be, or the expression is negative, but it only means that this is a fraction. So 3 plus h to -1 means 1 over 3 plus h. 3 to -1 means 1 over 3. Okay, what will be our next step? Very good. Thank you, Michelle. So the least common, oops. Please, let me draw your attention to something which I forgot to say. We started working on this limit. This was the function. We had to rationalize it, the numerator. This is 1. This over this is 1. So we didn't change the function, multiplying by 1. And notice that I copied the limit operator in the next stage. I copied the limit operator in the next step. I copied the limit operator in the next step. Only at the very last, the limit operator was applied and it goes away. Not here, not here, not here. But only when I replace x by -4 and I get this number. This is where the limit operator disappears. So we copy the limit. The next stage I have to copy the limit operator. In the next stage I have to copy the limit operator, and on and on and on and on till I get 1500. If you omit the limit operator, I can't give full credit for your work. So please make a note of it. Okay, so we found the least common denominator to be, and the denominator is h over 1. So we found the least common denominator to be,
Can't see everything, but it's like 3 times 3 plus.
right, there are two factors, they have nothing in common. It's 3 plus h. I still need it. Okay, so then the top of this one and the top of this one, what does this need?
3.
Good. And what does this need?
3 plus h.
3 plus h. Can anyone dictate the numerator?
3
Yes?
minus
Yes?
3 plus minus h.
Minus 3.
Minus 3 minus h.
Perfect. Now, whenever we determine the difference quotient, two things must happen. Can anyone refresh our memory on those two things that must happen? That's the second one. Very good. This h in the denominator will have to go away somehow with something from the top. But the first thing that has to happen at the top, all terms without h must go away. Because otherwise we will never be able to simplify that h in the denominator. So please keep that in mind. So of course that's true. I copy the top, which is negative h over 3 plus h, and times 1 over h. This is what I was expecting you to do today on that little quiz. This, right? So now I simplify the h. Please write 1 so you don't think that it's 0 in there. And now let's write it one more time so we can see it. Negative 1 over 3 plus h. This is what we applied the limit to. Now, and only now, I drop the limit operator. So please give me the answer.
Negative 1/9.
Very good. Do we all see the negative 1/9? Do we all see that since we applied h approaches 0, 3 plus 0 is 3, 3 times 3 is 9, negative 1 over 9, and this is when the limit operator goes away at the very last step. If you omit the limit operator, you understand this makes no sense. Limit of this to be that, it makes no sense. It's wrong. Is that clear? Okay. Now, I would like to just say one more thing about polynomial and rational functions and radical functions. There is a theorem. And this is the theorem that allows us to plug in. So if we find the limit of a polynomial as x approaches a, it's the same with just plugging in the polynomial in x, replacing x by a, where p of x is a polynomial. Another one is limit of a polynomial divided by another polynomial as x approaches a. We are allowed to write p of a over q of a. So this is a rational function. As long as q of a is not 0. And q of a is defined, of course. Otherwise, we can't. So if a is in the domain of this function, I can write that. If a is not in the domain of this function, that's even better and easier to say. If a is not in the domain of this function, I cannot do that. And this is true for anything else. Like, let's say, the square root. So limit of the square root of a function as x approaches a. It's the square root of f of a. Of course, a is in the domain of the square root of f of x. So basically, you can say now you are confusing us. Initially, you said that x does not equal a. Then you said plug it in to see what type of limit it is. Now you're saying that actually to determine the limit of a polynomial, rational, radical, etc., you plug it in as long as it's in the domain, because the answer will be the same. That's why. But we really mean it. When we say x approaches a, we really mean x does not equal a, for sure. Any questions? Any questions? I have one more theorem here that I need to talk about. And that is called the Squeeze Theorem. The Squeeze Theorem. Okay. So let's look at a scenario before we write what it is and when it's applied and so on and so forth. So let's suppose I have a function and I have another function. And these are my hands. This is the function at the top, the function at the bottom. And I have another function that is around a certain number, a. It's squeezed, it's sandwiched between the function at the top and the function at the bottom. If the limit of this function and the limit of this function, they both exist and they are the same, what will you say about the limit of the squeezed function as x approaches a? It's the same number, right? So now let's look at this. And why? Why do we even need this theorem? I'll explain in a moment. So let's say we have this scenario. Actually, I like the graph in the book. So I'm going to just show you directly the graph in the book. And I'm going to graph something there. So as you see, this is a function, x squared. This is another function, negative x squared. And let's assume that there is a function that right near a, in an open interval near a, which is 0 in this case, it's this red function. If the limit of x squared is 0 and the limit from negative x squared is 0, although I don't know anything about this red function, the limit from either side must be 0. There is no other way, right? Okay. So let's suppose this is a function, f of x. Let me call this one g. Doesn't matter really. And let's say we have this function that is f of x. And I have this one that does this. And this is function h of x. What are we interested in is finding the limit of h of x as x approaches a, of course. Here's a. This is what we don't know. But we have no mechanism for this. We cannot rationalize, we cannot use a product, we cannot use the limit laws, we cannot use a ratio. We have no idea how to solve this. If we manage to show that h of x is squeezed between f of x and g of x, we don't care what happens here. It can do this. But near a, h of x is squeezed between those functions. And number 2, the limit of f of x as x approaches a and the limit of g of x as x approaches a exist. And they are the same number, let's say L. These are the two hypotheses of the Squeeze theorem. I need to show that the function I'm trying to find the limit from is squeezed between these two functions near a. I don't care what happens outside or far away. If the second hypothesis, the limits from the either functions, they both exist and they are both equal to the same number, then I will say by the Squeeze theorem, what do I conclude? That the limit of h of x as x approaches a must be. That's it. It's squeezed between those two functions near a. Those two functions have a limit that is the same and exists and is the same. Therefore, the function I'm looking for to find the limit for must exist. And it must be L. Does it make sense? Okay, so let's choose a problem. So use the Squeeze theorem, that's 36. Use the proof and so on and so forth, and prove this, and blah, blah, blah. 1, 2,
40.
which one?
40.
Oh, you said 40? Very good. So let's look at 40. We have limit of the square root of x as x approaches 0 from the right, multiplied by e raised to sine pi over x. They want us to find this limit. What is the limit of this? The square root of 0 from this right-hand side is 0. What is the limit of this? This pi over x, as x approaches 0 from the right, we graphed it a minute ago, or 2, or half an hour. This is infinity. How much is sine of infinity? D&E are oscillating. It's between 0 and 1, between -1 and 1 all the time. I have no idea. So I have no technique. I have absolutely no technique in determining this other than the squeeze theorem. But here is our starting point. We know that sine pi over x, or sine in general, is a bounded function. Is one of the nice functions. It cannot go above blah, blah, blah. It cannot go below blah, blah, blah. What do I mean by blah, blah, blah? Very good. So we know that sine of any angle must be somewhere between -1 and 1. It cannot be anything else. Agreed so far? Okay. Now, I'm trying to build this function. Remember the graph of e to the x. Here's the graph of e to the x. We have to put it especially separately in our notebook. This is the graph of e to the x. I'm trying to build e raised to sine pi over x. So this is an increasing function. We are talking about 0 from the right. So we are talking about this side, 0 from the right. Now, 0 from the right, what does sine do? Let's also picture the graph of sine. Because if sine is decreasing, there's one story. If sine is increasing, it's a different story. Well, but I know that around 0, on the positive side of 0, sine is increasing. When we talk about this, we're not talking about this, somewhere here. We're talking about very close, right? 0, x approaches 0 from the right. So the function is increasing. So coming back to our situation here, what do you think e to sine pi over x will be? Squeezed between. Say it again.
0.
Well, we have to. So now, I really have to drop this portion because I'm getting into a little bit of a trouble. Because here, it's still increasing on this portion between -1 and 1, but for x between -1 and 1, the function is increasing. But I'd rather just look on the right-hand side if you want. So this side, e to this, must be less than e to the first power. And must be less than e to negative. We can look at both sides, really. It's increasing around 0. It's increasing function. This is increasing, and e to -1, e to sine pi over x, and e to the first power. Everything is increasing. Okay, so we came up with this piece, but now I have one more piece to worry about. Now, can I multiply all three sides by the square root of x? The answer is yes, only if the square root of x is never 0, and yes, if a square root of x is positive. I don't switch the symbols, but if the square root of x is negative, then I have to switch the symbols. Is the square root of x positive? Is the square root of x 0? No. So then I will write the square root of x times e to negative 1 less than or equal to the square root of x times e to sine pi over x less than or equal to the square root of x times e. I found two functions. I found the bottom function, which is f of x, and I found the top function, which is g of x. So for now, I only proved one hypothesis. I proved that the function that I want to determine the limit from is squeezed between two functions near 0, on the right-hand side of 0. So that was number 1. Number 2, now I have to find the limit of e to negative 1 the square root of x when x approaches 0 from the right. I have to find the limit of e times the square root of x when x approaches 0 from the right, of g of x and of f of x. If these two exist and are the same, so is, I just determined the limit of h of x. So where does this go?
Well, e is constant. So
0 from the right. Where does this go? We just wrote it here, right? As x approaches 0 from the right, the square root of x goes where? Good. So where does this go?
0.
Of course. It's a constant times 0. Where does this go? 0. From 1 and 2. From 1 and 2 by the Squeeze Theorem, limit of the square root of x e to sine pi x as x approaches 0 from the right must be guaranteed what?
0.
Of course. So we show that it's squeezed between two functions. We show that the limits of those two functions exist and they are the same. Therefore, by the Squeeze theorem, the limit must be 0. And there is no other way of determining this limit unless you just plug in numbers in the graphing calculator.